Okay, now when we're representing atoms, we can represent atoms by their electron structure or the electron configuration. Take hydrogen, for instance. When we write it out, the electron configuration, since it only has one electron, it starts in the 1s. We follow the Aufbau principle. It starts with the lowest energy level, which that's 1. The S would be our subshell, our suborbital, and we see that that's our S, and then we see the number of electrons would be 1. So that's how we write it. Energy level, that's our orbital, and that is our number of electrons. Remember that S can hold 2, P can hold 6, D can hold 10, and F can hold 14. Okay, so we'll take fluorine for example, and let's look. This is the electron configuration for it. Let's look at our periodic table and see how we got that. So here's our periodic table, and remember, when we're looking at this, all we have to do is we subtracted our D, subtract 1, and from our F we subtract 2. But we see that fluorine is, we erased our P. We'll bring that guy back so we can see that there. And we see our P block is in red. Okay, now fluorine is right here. Okay, so to find this electron configuration, all we do is we follow the order. So 1, which is right here, and then this is S block, so 1s1, which would be right there, then 1s2. So we write it out and we go 1s2, and this we keep going. What comes after that one? We go 2s and then 1, 2, and that's where we go 2s2, and then we keep going and we see we come over here and we get 2p. We have 1, 2, 3, 4, 5, and we got to fluorine. So our electron configuration is 1s2, 2s2, 2p5. Okay, so what we're saying is that all of those energy levels, in the first energy level it's completely full, and in the second energy level we see that we have a total of 7 electrons. 2 of them in their S, and 2 of them, or 5 of them, are in the P. And so we can see our electron configuration written out like that. Okay, so that's how we get this right here. So let's look at if we have larger. That can get really, really big. So if we're looking at our periodic table and say we were doing something that was, had 86 electrons, okay, that's a huge amount of 1s2s, 2s2s, 2p6, and all of those, and it just keeps going on and on and on and on and on for a long time. And so what we do is to make a shortcut. We write out electron structures, and they're tedious, but we write them out, and basically what we can do is we call this the noble gas notation, or the noble gas shortcut, or whatever we have, is that what we can say is we can take the electrons that the noble gas equals, like argon represents 18 electrons if you look on the periodic table. So basically by writing argon like this, we can take out all this first part. So see how we have 2 here, 6 there. So 2 plus 2 is 4, 4 plus 6 is 10, plus 2 is 12, plus 6 is 18. Well, we can take out, basically we don't have to write all of this first part, all those first 18 electrons, and we just write argon. And then we just write what comes after argon, which would be 4s1. So if we look on our periodic table, the way that you can think of this is when you're referring to your periodic table, okay, whatever I am writing, I can always look at the noble gas that's behind it. So say I was writing something really big. Say I was writing francium that had 87 electrons. So instead of writing 1s1, 2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s2, and keeping going all like that, all I have to do is what noble gas is right behind francium. Well, that's 87. What's 86? What's radon? So all I'd have to do for francium, instead of writing all that other stuff out, I just write Rn, put it in brackets. That gets me all the way to this point right here. That took care of 86 electrons. So then I just start here, and that's 7s1. So instead of writing the entire thing out, we take the shortcut and just write the noble gas notation. Okay? And that makes it a lot quicker, a lot fast. using our periodic table and using the noble gas notation. So let's look at an example. It says that an atom with 34 protons has the electron structure of the notation below. And it says write the proper atomic ionic notation. So when we are looking at this, first of all, we have 34 protons. Okay, that's going to be our atomic number. We have our 34 protons, and then if you look, we have 2, 4, 10, 12, 18, 28, 30, 36. We have 36 electrons. Okay, so we have 34 protons, 36 electrons, so we're going to have more electrons than we do protons, so we're definitely going to have that -2 charge. So all we have to do is look on our periodic table and see what has 34, which that would be our selenium, which would be Se. That's the element that we're dealing with, so we have Se. And then basically we have a -2 charge. Because 34 protons gives us selenium, and then we counted up all of our electrons, which is 36, which is the difference of 2. Okay, next example, it says write out the appropriate nuclear symbol notation and electron structure for the non-ionized, so we don't have a positive or negative atom shown below. So we're looking at this, we see the blue dots are going to be protons, so we count those up. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 protons. So we can look on our periodic table, and we see that 8 protons is going to give us oxygen. There's our oxygen. So we know that our symbol is going to be oxygen. Okay, so we write O. Now, for oxygen, we see we have 8 protons, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8 protons, 10 neutrons. So give us a mass number of 18 all over 8. So that's oxygen 18. That is our nuclear symbol notation. Now our electron structure for this, we're trying to find our electron configuration for this, so let's use our periodic table because that's the easiest way to do it. So let's look at our periodic table, erase some of our old stuff, and we're trying to find the electron configuration for oxygen. Let me draw P block back there. There's P. So all we do, like always, start at the top. So this is 1 S block, 1, 2. So we have our 1 S2. And then we keep going. We have 2S, 1, 2. 2S2. Then keep going over here. This is 2. Remember that's P block, and 1, 2, 3, 4. So we have 2P4. That's our electron structure for it. To check and make sure we have it right, we know we have 8 protons, and it's non-ionized, so they're going to be 8 electrons. So 2 plus 2 is 4 plus 4 is 8. We did it right, and that would be our electron configuration.